The technical report we're diving into today is called K-EXAONE Technical Report, Journey to Frontier-Level Performance of Foundation Models. It's a really deep paper from LG AI Research on their new large-scale multilingual LLM.
It's a big one. For everyone who wants a quick version, here's the 1-minute summary of what makes this model tick. K-EXAONE is really all about getting to that frontier-level performance, but they've built it around an architecture that's defined by both scale and some serious efficiency.
Right, that efficiency really comes from their use of mixture of experts, or MoE. I mean, the model has a massive 236 billion total parameters, which sounds huge.
It is huge.
But the key is that it only activates a tiny fraction of that, just 23 billion parameters, when it's actually running inference. And that ratio is what makes a model like this actually deployable.
And, another huge headline here is the context length. This thing supports an enormous 256K token context window. That's achieved with a pretty sophisticated hybrid attention mechanism they designed specifically to handle that kind of scale.
And it's not just big, it's broad. K-EXAONE is seriously multilingual. We're talking 6 core languages: Korean, English, Spanish, German, Japanese, and Vietnamese. So real international reach.
And finally, the performance. The evaluations basically show K-EXAONE is competitive against other big open-weight models. It holds its own across reasoning, agentic tasks, general benchmarks, and of course a whole suite of very tough Korean and multilingual tests. It really establishes it as a powerful proprietary foundation model.
Okay, that's the perfect setup. So let's unpack the architecture first, because the way they implemented MoE seems to be where a lot of the engineering magic is. This isn't like the older, dense EXAONE model.
No, if he completely shifted to a fine-grained, sparse MoE design.
And the goal there was high capacity without, killing the throughput.
Exactly. The setup uses a big pool of 128 total experts. But for any given token, the router only picks 9 of them to be active. So you get 8 experts that are specifically routed for that token, plus 1 shared expert that handles more general stuff.
So just to spell it out for you, you're getting the brain power of a 236 billion parameter model, but with the speed and cost of a 23 billion parameter one. That's the whole efficiency pitch.
That's it.
But MoE systems are notoriously difficult to stabilize during training. So how did they deal with the routing? How do you keep it stable?
That's a great question. Because expert imbalance can just completely wreck an MoE model, where a few experts get all the work. They used 2 main tricks. First was sequence-level load balancing, which just spreads the work out evenly.
And second?
Second, they used a dropless routing policy.
Dropless routing? That sounds like a traffic system that makes sure no data packets get lost on the highway. What's it actually doing?
That's a perfect analogy. In some Spark models, the router might just drop a token if it can't find a good expert for it. And that messes with the gradient flow. Dropless routing guarantees every single token gets sent to a set of experts. It just makes the whole training process way more stable.
Okay, speaking of speed, let's talk about their other big innovation here. The multi-token prediction module, or MTP. This is all about inference throughput, right?
Right. MTP is this small auxiliary dense layer. It's only about 500 million parameters, and it's trained to do one thing, predict several future tokens all at once.
And what's the payoff in practice?
During inference, K-EXAONE uses that MTP block for something they call self-drafting. So think of it like this. The MTP module quickly drafts the next few tokens, and then the main decoder just has to verify and accept them. It lets the model jump forward instead of going 1 token at a time.
And that gives you what, a big speed boost?
It gives them about a 1.5x improvement in decoding throughput over standard autoregressive decoding. It's a pure speed play, and it works.
Okay, that covers speed and efficiency. Let's shift gears to that massive 256K context window. Building in a MoE model is hard enough, but one that can also handle a document the size of a novel that requires some serious architectural work.
It really does. And they leaned heavily on their hybrid attention architecture. Of the 48 total layers, they have this mix. 12 are global attention layers, which can see the entire context, and the rest. The other 36 layers use sliding window attention, or SWA, which only looks at a small local neighborhood of tokens. It's really the only way to manage the compute cost at 256K.
But the memory bottleneck is always the KV cache. What was their solution for that?
They did something really aggressive. They slashed the SWA window size from a pretty standard 4,096 tokens all the way down to just 128.
Wait, 128, that's a 32-fold reduction? I mean, how does the model not just completely lose track of the local context with a window that small?
That's where their stabilization techniques become absolutely critical. First, they use something called QK norm. It's just layer normalization applied directly to the query and key vectors. This helps prevent what's known as attention logit explosion, a common problem when you have these super deep networks and really long inputs.
So QK norm keeps the math stable. But how do they make sure the model could still generalize all the way out to 256K?
By being very clever about where they applied rotary position embeddings, or rope. Instead of applying rope everywhere, they only applied it to the SWA layers.
Why only there?
Because ropey is what helps the model extrapolate to longer sequence lengths. By keeping it just on the SWA layers, they let it do its job for long-range reasoning without interfering with the global view from the global attention layers. Those two things, QK norm and selective rope, are what let them get away with that tiny SWA window.
That's fascinating. Okay, let's talk about the data in Tokenizer, because they had to upgrade it significantly to handle all the new languages and domains.
Oh yeah, they redesigned it completely. They boosted the vocabulary size from 100K to 150K. And that extra 50K wasn't random. It was specifically for better coverage in German, Japanese, Vietnamese, and also for technical domains like STEM and code.
And they got a pretty wild efficiency gain from this, right? Something like 30% on average. How do you get that much of a boost just from the Tokenizer?
It's all down to a strategy called Super BPE. Super BPE introduces superword tokens. These basically treat common phrases or technical terms as a single token. Since about 20% of their new vocabulary is made of these superwords, it just drastically shortens the sequence length for any given text.
And shorter sequences mean less computation. Simple as that.
Exactly. It's a direct path to that 30% efficiency gain.
They also made a really subtle but important change to Unicode normalization switching from NFKC to NFC. Why does that matter for a technical model?
For regular text, it barely matters.
All right.
But for things like code or math, it's crucial. NFC preserves things like superscripts. So under NFKC, the equation EMCT might get flattened to EMC2.
Which would obviously confuse the model.
Totally. Switching to NFC keeps those critical semantic details intact, which is essential for accuracy in STEM fields.
All right, that paints a clear picture of the architecture. Let's move to the training process itself. This thing was trained on 11 trillion tokens. The compute number is just $1.52 times 10^10 FLOPs. It's a reminder of how massive these projects are.
It's an incredible investment. They used a 3-stage pre-training curriculum to build up its knowledge. And a huge part of managing that cost was training natively in FP8 precision. The paper shows they got loss curves comparable to BF16, so they got all the efficiency of FP8 without losing stability.
Now, when you add 3 new languages, data imbalance becomes a huge problem. How did they make sure German, Japanese, and Vietnamese got enough quality training without, watering down the model's existing strengths in Korean or English?
They used targeted data synthesis. So instead of just dumping in new data, they focused on cross-lingual knowledge transfer. They generated synthetic data designed to help the model learn a concept in one language, say English, and then apply that same reasoning in another, like Vietnamese.
And that leads right into this idea of thinking augmented data synthesis. This sounds like their secret sauce for better reasoning. What are thinking trajectories?
It's essentially teaching the model the process of reasoning, not just the final answer. They generated these step-by-step inference paths for problems, and then baked those paths right into the training data. So the model doesn't just see question A and answer Z.
It sees the path, A to B, B to C, all the way to Z.
Exactly. And that explicit supervision is what helps it learn complex reasoning behaviors much more effectively.
Let's talk about that 2-stage process for getting to 256K context. They started with an 8K base model. This is where a lot of long context models can stumble and forget how to handle short inputs.
Right. The process had to be really careful. Stage 1 went from 8K to 32K. Then stage 2 was the big leap from 32K all the way up to 256K using more and more long document samples. And like you said, the biggest risk is catastrophic forgetting of short context performance.
So what was their mitigation for that? How did they stop it from happening?
They used a rehearsal data set in both stages. It's just a curated set of high-quality, short context examples from the original pre-training data. It acts as an anchor, constantly reminding the model how to perform on shorter tasks while it's learning to handle massive ones.
And they added another data set too, right? For reasoning.
Yes, a synthetic reasoning data set. This was full of tough math, science, and coding problems to make sure its reasoning abilities didn't degrade under the strain of processing such long inputs.
And the final check, the gold standard for long context, is the needle in a haystack test.
That's right, the NIAH test. Can the model find one specific sentence buried in a giant document? They said they kept iterating on the training and stabilization until they got near-perfect NIAH performance. That's what gave them the confidence in that final 256K number.
Okay, that brings us to PERS training. This is where you turn a raw model into a useful product. They used SFT, RL, and preference learning. Starting with supervised fine-tuning, they really focused on boosting Korean capabilities.
They did. For FFT, which is all about instruction following, they used a ton of institutional data from K-Data, the Korea Data Industry Promotion Agency. They turned it into high-quality question answering and translation data sets to make sure the model had deep, specialized skills in Korean.
Now, here's where things get really cost-effective. Training an agent to use tools like a web browser is incredibly expensive if you use humans. How did they get around that?
They were really smart about it. They used other LLMs to build synthetic tool environments. Basically, they had models generate thousands of tool use scenarios, complete with verifiable success criteria. Then they'd pre-filter the bad or unsolvable ones, leaving them with a huge, clean data set for agent training at a fraction of the cost.
And for a real-world agent, context management is everything. They came up with a neat solution for web search using 2 sub-agents.
Yeah, this is great, because in a long agent workflow, the context window fills up with junk really fast. So their first subagent is a summarizer. It just boils down long web pages into the useful bits. The second one is a trajectory compressor. After a few tool calls, it collapses the whole history into one clean JSON object, which saves a ton of space.
Let's touch on the alignment objectives. For reinforcement learning, they use something called agapio.
Right, agapio. It's a type of off-policy gradient. But what that really means for you is that it's a clever way to recycle training data. RL is super data hungry, but agapio lets them reuse older training steps safely, which speeds up the whole process.
And they made a key decision to freeze the MoE router during RL. Why was that so important?
It just stabilizes the whole process. If the router is changing paths while the policy is learning new behaviors, things can get chaotic really fast. Freezing the router lets the policy learn much more efficiently.
And finally, for preference alignment, making it good at chat and creative writing, they proposed a new method called grouper.
Grouper is their improvement on an existing method. The key idea is that it combines human preference data with synthetic rewards from things like rule-based verifiers. The goal is super important. Get strong alignment with what humans want to see, but without damaging all the hard-won reasoning performance from the earlier stages.
That gives us a great map of how K-EXAONE was built. Now for the big question, how does it actually perform? What stood out from the evaluation results?
It's extremely competitive, especially when you remember its efficient inference size. On reasoning benchmarks, it got really strong scores, like 83.8 on MLU-PRO and 79.1 on GPQA Diamond. In math, it actually surpassed some big baselines, hitting an impressive 92.8 on the ANY 2025 metric.
And the agentic encoding performance, that's what really matters for practical industrial use cases.
Absolutely. It scored an 80.7 on LiveCodeBench v6 for coding and showed real promise on SweBench Verified, which tests automated software development. And its long context reasoning held up too, confirming all that architectural work paid off.
What about its core mission of being multilingual? How did it do there?
He was dominant in Korean, scoring 67.3 on KMMLU-PRO for professional knowledge, and a huge 86.8 on the Korean long context benchmark. And across all 6 languages, it did great, with a 90.5 average on the WMT24++ translation test. The gains were really evenly spread.
Okay, finally, let's talk about safety. This might be the most unique part of the paper, the KAUT, or Korea Augmented Universal Taxonomy. Why did they feel the need to create a whole new safety framework?
Well, the paper argues that most existing AI safety frameworks are, frankly, Western-centric. They don't always capture the specific cultural or legal nuances of other regions. KAUT was designed to fix that by creating an ethical framework that is specifically tailored to the Korean context.
So what does that framework actually cover? What makes the Korean sensitivity domain so necessary?
KAUT has 4 main domains: universal human values, social safety, future risk, and that critical 4th one, Korean sensitivity. This domain is designed to handle sensitive local topics, things involving history or geopolitical conflicts. It ensures the model adheres to domestic laws, like the national security law, and relies on verified historical records. It's a systematic attempt to prevent harmful, context-unaware responses on topics specific to that region.
But when they tested the model on their new benchmark, KGC safety, how did it do?
It was incredibly effective. The benchmark is comprehensive, 2,260 test cases. K-EXAONE got a safe rate of 96.1%. And for context, its predecessor was at just 58%.
Wow, that's a massive jump.
It is. And the key finding was that most other models performed their worst, specifically in the future risk and Korean sensitivity categories. It really validated their approach and showed that this targeted framework was mitigating the exact problems they designed it to solve.
So if we zoom out, K-EXAONE is this powerful combination of a high-capacity MoE architecture, hybrid long-context attention, and a really advanced targeted training plan. The result is efficient, competitive, frontier-level performance.
That's the story. It's a powerful proprietary model. And of course, the report is upfront about the standard LLM limitations. It can still be biased or factually incorrect, and its knowledge is frozen in time.
And they make a clear point about compliance, noting the model went through LG's internal reviews and the license requires users to use it ethically and responsibly.
Right. But I think the biggest takeaway for the industry is really about that safety framework. KAT is this successful proof of concept for integrating local, sovereign, cultural, and legal sensitivities, in this case Korean ones, with global ethical standards into a real, verifiable benchmark.
And that leaves a really interesting question for you, the listener, to think about. Does this systematic integration of specific sovereign cultural context into safety benchmarks represent the future standard for building robust and reliable foundation models around the world? It seems like it could be essential for any company that wants to deploy globally while still acting responsibly at a local level.